Energy is one of the most important concepts in the world of science. Here, we will develop a better understanding of energy and how to quantify it. Energy is present in the universe in a variety of forms and origins. We talk about mechanical, chemical, electromagnetic, or nuclear energy. Even the inert mass of everyday matter contains a very large amount of energy. Although energy can be transformed from one kind to another, all observations and experiments to date suggest that the total amount of energy in the universe never changes. And this is a strong law or principle of physics that has led to important discoveries. This is also true for an isolated system. If one form of energy in the system decreases, then another form of energy in the system must increase. For example, if the system consists of a motor connected to a battery, the battery converts chemical energy into electrical energy, and the motor converts electrical energy to mechanical energy. Understanding how energy changes from one form to another is essential in science. We will be talking about mechanical energy, which is the sum of the kinetic energy, the energy associated with motion, and potential energy, which is the energy associated with relative position. Using an energy approach to solve certain problems is often much easier than using forces and Newton's laws. These two very different approaches are linked together through the concept of work. Work has a different meaning in physics than it does in everyday usage. In physics, work is done only if an object is moved through some displacement while a force is applied to it. The work W done on an object by a constant force during a linear displacement is given by work is equal to the scalar product of the force times the displacement. SI unit in this case is joule. Pay attention to the scalar product of the force and the displacement. Only parallel components contribute to the work. If you have a force which is perpendicular to the displacement, then that force is not doing any work. Only if there is a component which is parallel to the displacement, then that parallel component is going to do work. If you hold something vertically and there is no displacement, you don't do any work, even though you get tired of holding something. Work can be positive and negative. Look at the equation. It will depend on the sign of the cosine. Let's do now an exercise. A Minnesotan girl returning from a successful ice fishing trip pulls a sledge loaded with salmon. The total mass of the sled and salmon is 50 kilograms, and the girl exerts a force of 120 newtons on the sled by pulling on the rope. First, how much work does she do on the sled if the rope is horizontal to the ground and she pulls the sled 5 meters? Then, how much work does she do on the sled if the rope makes an angle of 30 degrees and she pulls the same distance? First, let's draw the free body diagram with the forces that we have here: the weight, the normal, and the force done by the girl. In order to calculate the work, we only need to multiply the force times the displacement, F delta x, which in this case is 120 newtons by 5 meters, and this gives us a work of 600 joules. For the second case, the free body diagram has to consider that the force is not parallel to the displacement, but there is an angle of 30 degrees with the horizontal. In order to calculate the work, because only the parallel component of the force parallel to the displacement takes place here, or only contributes to the work, we have to project the force, that is, just multiply the force by the cosine of 30 degrees in this case times the displacement delta x. So this is 120 newtons times 0.866, which is the cosine of 30 degrees and those 5 meters, and this gives us a total work of 500 and 20 joules.